give a perspective that we haven't had so far in the Living Lab about climate services from the point of view of international organizations such as the Food and Agriculture Organization of the United Nations and the World Food Programme. The first one will be by Ms. Federica Matteoli. Federica has 15 years experience in the field of climate change, political science, and participatory approaches in international agencies, as I said, such as FAO and the World Bank, as well as government agencies. She has collaborated with the Global Alliance for Climate Smart Agriculture since 2014. She is leader of Climate Smart Agriculture team at FAO, and she is coordinator of a project that supports FAO knowledge activities on climate smart agriculture and projects at the field level in Botswana and Ecuador. She coordinated an FAO project on communication for development on climate change in Bolivia, Democratic Republic of Congo, and in the Caribbean. She worked for the World Bank on climate change matters, and she has a degree in law, a master on international cooperation, and a PhD on science and management of climate change. So I would say a perfect match for our Living Lab. And she will talk about climate smart agriculture services to protect biodiversity and environment, and the role of political choices, because there's places on our planet where the natural capital has a very important role when we talk about climate services. So I would pass it on to Federica. Welcome again, and please address our audience. Thanks, Federica.
Thank you very much, Luigi, and everybody for this invitation. Let me share the screen so I have my presentation. Can you see the presentation?
Yes.
Yes.
Can you hear me very well?
Yeah, very well.
Okay, good. Let me start with this presentation that I would like to share with you some approaches, tools, ideas related to climate smart agriculture and climate services. How these two approach and tools can protect biodiversity environment, and I would like to share with you the concept on what is the role of political choices, the importance of these important element in environment and biodiversity and development. Let me start with the concept. What is climate smart agriculture? Climate smart agriculture is an approach developed by FAO in 2010 in collaboration with other institutions, organizations, and governments, and NGOs and CSOs institutions. It's based on three elements, on three pillars. The first one is the approach should increase the sustainable agriculture productivity and the incomes. The second element is based on the adaptation and resilience, building adaptation and resilience of people and food systems to climate change. And the third element is based on reduce and remove greenhouse gas emissions where possible. So the approach is based on these two elements: productivity, sustainable productivity, and actions to adapt and reduce climate change. This process, this approach is at the base to guide the transformation and the reorientation of agricultural systems to ensure food security in the context of climate change. It's not a list of practices that are applicable everywhere. Is a context and location specific. This means that what can be a climate smart solution in one place is not necessarily so in a different location or context. So, and CSA works at multiple scales, works at the plot level, farm level, community, landscape, river basin scale, and of course the political and institutional level. So it's more a concept where practices can be recognized as a climate smart because they help farmers to increase sustainable productivity and income and adapt to climate change and reduce greenhouse gas emissions. Let me share with you some practices that to protect biodiversity and environment that can be recognized as climate smart agriculture. The first one is agroforestry. FAO developed in 2014 a project on agroforestry in the Central America Dry Corridor. The characteristic of this project, of these practices, agroforestry, is that the project can integrate ancestral practices with scientific knowledge. There was a crop production combined with multi-purpose trees dispersed in the plot, and no tillage was used, and mulching of crop residues and cutting from trees and shrubs was used alternative to the locally widespread slash and burn practice. What are the benefits of this project? First, reduce pressure on forest. The project reduced erosion and the loss of topsoil. There was an improvement of water retention and the soil humidity. In Honduras, for example, the humidity increase of up to 20%. And there was an increase of crop yields. In Guatemala, maize improved the production of 55%, and the beans 46%. And there was an increase of soil fertility and carbon sequestration. Another practices that can be recognized as a climate smart agriculture is different practices. For example, varietal mixtures, intercropping, crop rotations, and this can help on having diversification of farm income, a great resilience to pests and diseases, also under climate change conditions, and enhanced ecosystem service and production factor. As you can see, these two practices pose the attention to the three elements of climate smart agriculture: sustainable productivity, adaptation to climate change, and mitigation to climate change. However, these practices can help on protect biodiversity and environment. But in order to create an efficient system to tackle the climate change, we need to integrate the use of these practices in an holistic approach, whereby all aspects of system are strengthened, such as climate services, political decisions, and capacity building. This, especially if we want to support farmers that are the real beneficiaries of our efforts. This is why FAO produced this CSA implementation process in the 5 actions. The first one is expanding the evidence base. I'm in the next slide. I will explain you better what is expanding the evidence base. But it is essentially having an assessment of the situation. What are the climate change impacts? What are the baseline scenario? What are the costs of implementation and barriers to adoption? The second action is supporting enabling policy frameworks. Why? Because in many countries, we have already climate change frameworks, but they are not, there are gaps related to agriculture, for example, or related to climate services. The third element is strengthening national and local institutions. In many countries, especially developing countries, for example, extension services collapsed, and there are not the link between the governments, the center of research, and farmers. And another element, absolutely important, is enhancing financing options to support, for example, the transformation of agricultural systems from the traditional to the new one. How we can support farmers at the financial level in this transformation. For example, how climate services, the technologies related to climate services can be supported at the financial level. The third element is, of course, implementing practices at the field level. How these practices can be used at the field level to support farmers in this transformation. And all of these actions should be monitored and evaluated. Now I would like to share with you a video on climate services for farmers. It's an important video, I think, because to understand how FAO works with climate services to support farmers. I don't know, Luigi, if I have to stay in sharing the desk, or I can stop.
You should stop sharing, otherwise okay. I'm not going to be able to do it.
Okay, good. I stop it.
Okay. So let's see if we manage to make it.
I put the link to the video over there in the chat. This is the right link, Federica?
Yes.
Okay.
It is.
In a warming world, changing climate conditions threaten livelihoods and ecosystems. Those hardest hit by climate change are food insecure people with little means to cope or adapt. The number of undernourished and food insecure people is on the rise after decades of decline. Key drivers of this trend include conflict, climate variability, and extreme events. In developing countries, climate-related disasters are responsible for 26% of damage and loss in the agriculture sectors. Now, more than ever, we need to act to support those most vulnerable. Timely advice and early warning systems can help farmers to prepare for and respond to climate impacts. The economic and social benefits of investing in prevention and preparedness are clear, with a cost-benefit ratio of 10:1. Advances in technologies and innovation provide new opportunities for the dissemination of alerts and advisories to farmers and rural dwellers to make sure the information reaches those most vulnerable, including women and youth. Together with national and international partners, the Food and Agriculture Organization of the United Nations supports countries to strengthen climate services for farmers, from monitoring and data collection to dissemination of actionable advice to end users, and empowering farmers to make climate-smart decisions through participatory approaches. Getting there is a country-specific, step-by-step process. Here are some of the steps. improved monitoring and data collection. Installing weather stations equipped with agricultural parameters will improve the coverage of quality information relevant for agro-weather services. Agricultural and meteorological data can be shared in a common database. Creating working groups of national entities, including ministries and research institutions, will establish data sharing and co-production of outputs. Service production. An agroclimate service is produced when data from stations or satellites is processed and analyzed to create actionable alerts, recommendations, or advisories in a way that can be easily applied by end users. For example, agroclimate data can be used to forecast pest and disease outbreaks for early response and management. Actions based on timely and accurate information can be preventative rather than reactive. Dissemination to end users. Alerts and advice for farmers can be shared through bulletin, radio, SMS, smartphone application, social media, or web platform. Advances in technology and increased access to mobile phones provide new opportunities for climate services to reach end users. Decision-making and action. Using targeted alerts and advisories can improve the resilience of farm communities. Through participatory trainings, farmers learn how to apply climate information to identify actions best suited to the local climate and individual circumstances. Achieving a world with zero hunger by 2030 requires concerted effort and ambitious climate action. Climate services can support the agriculture sector and, importantly, farmers to prepare for and prevent the impacts of climate change. Let's work together to support farmers and countries to reach their climate and food security goals.
Thank you, Luigi.
You're welcome.
So let me share again the presentation. But in this video, it's clear how the climate services can be used to prepare for and prevent the impact of climate change. Decision making and actions. May I share? I think Luigi, we lost Luigi. No. So in this video, it's important to understand that decision-making and action can improve resilience of communities. But we need to improve, for example, monitoring and data collection, to create working groups at the national entities. These help on identifying the assessment, they identify yeah, okay, good. I can share the screen.
Federica, just to remind you that you have 5 minutes left.
Okay, so this video is important because in 4 minutes we have how we can prepare for and prevent the impact on climate change using climate services. In the last slides, I told you about the process to implement climate smart agriculture. Why is important expanding the evidence base? Because in this step, in this action, we need to assess the situation. Why is important? The evidence allows to identify and assess the situation, especially the suitable and effectiveness of climate change adaptation and mitigation for agriculture. We need to answer some questions when we start climate smart agriculture. What are the impacts that we need to adapt to? What are the vulnerabilities? What are the highest potential for greenhouse gas emissions reduction or creation of carbon sinks? These are identified answer the question, we can identify the climate change adaptation and mitigation options that are economically viable and socially acceptable. There are many tools that can help on that, but I want to focus on two in particular, Mosaic and X-Act, because Mosaic is an innovative approach as an ideal tool to carry out climate change impact assessment studies at the national level. Information on the impact of climate change is a primary resource for policymakers trying to cope with climate change. The models integrated in Mosaic are 5, but I want to concentrate more on the climate component. The climate component of Mosaic include tools that make local climate projections of different agroclimatic variables. For example, the minimum and maximum temperatures, the precipitation, resources evapotranspiration, and growing season onset and length of the growing season. Fact is another tool developed by FAO that can help on how to mitigate and how much mitigate the impact of climate change. For example, it provides ex-ante estimates of the impact of land uses and the land use changes on greenhouse gas emissions and carbon sequestration. That illustrates the impact of suggested activities where the carbon balance is selected at the climate change mitigation indicator. This tool is applicable on investment projects, value chains, and then the policy scenarios. Let me share with you 2 case studies where climate services are used at the field level, and how the use of these climate services are used in this project. We use also the 5 action process for climate smart agriculture. This holistic approach in Tajikistan, for example, we use is a EU-funded project implemented by FAO, where the pilot AgroMet network acts as a sensitization tool to bring together key institutions required to produce climate services in agriculture. There are barriers, and with the support of FAO, the implementation of this project, we try to reduce these barriers. For example, FAO installed 3 new stations in agricultural regions identified by national experts, and developing capacity and knowledge to collect and produce AgroMet products to end users and link to NGOs for dissemination. And we increase also capacity building for national institutions. You can see that the expanded evidence base is used to see the situation, so to identify the barriers. The other actions of the process, for example, strengthening the capacity building, identify the financial support, and the framework, policy frameworks was analyzed to identify the actions to react to these barriers. And the field and the developing this project at the field level helped on that. The other project is in Kenya, where the climate services was used to specific agricultural practices or commodities, where was identified as a key request by farmers to make the products actionable on the ground. There was barriers on that, specifically to the climate services are not sufficiently tailored to farmers and practices and needs. and where they are sufficient and not used. This is one of these barriers. And FAO, this project in Kenya, identified the collaboration to develop tailored climate services for tea producers in Kenya, one of the key elements. And also the collaboration between these institutions can help on share information on products, on services related to tea. And cellular alert that support farmers adjust the time of sowing and harvesting are provided to tea producers. Some conclusions. So in these examples, we can say that before designing new climate-sensitive policies actions, policymakers should assess the situation. So identify the climate impacts. What is more, if we have already adaptation actions or greenhouse gas emissions reduction actions, what is the vulnerability, the mitigation potential? We need to identify and evaluate potential climate smart options and what are the climate services that can support these assessment and these options. What is the baseline scenario? What are the synergies and trade-offs? We need to determine the institutional and financing needs. If we can have support by international entities like Green Climate Funds or GEF, what are the costs of this implementation? New policies need to fill the policy gaps related to agriculture and climate change. And what are the support that the government can give to climate services. For example, if we have already the meteorological institutions, how these can be supported by governments or creating a group of works or on specific topics. We need to strengthen in national and local institutions. For example, as I told you, extension services in many countries are completely collapsed. And we need to identify how to recreate the extension services or change completely the attention, not only to institution or the governmental services, extension services, or use, for example, NGOs or center of research that are private could be a solution. What are the climate information services available, or how we can improve, strengthen these services? For example, another important element is enhancing financing options. Integration of climate smart agriculture and climate change and climate service into sectoral budgeting at the domestic level, for example. What are the roles that can play the private sector investments, the financial services? Time ago, we had an exchange of ideas with Rabobank, for example, in how the private sector can support climate services or climate agriculture and smart agriculture actions. Another important element is understanding the socioeconomic and gender differentiated barriers and what are the mechanisms to incentivize the adoption of climate smart agriculture practices to design and implement supportive policies. For example, what are the best insurance that the government or the collaboration between the government and the private sector can support farmers on adopting climate-smart agriculture practices. Fundamental in all this process is the involvement of all stakeholders from the beginning of the process, and elaborate communication strategies. For climate services, for example, what is the best tools to use to inform people? Is a mobile phone, social media, TV, all the countries and the areas inside the countries can have different solutions for that. Draw on knowledge of local producers. For example, what is the central indigenous knowledge that can be supported to create this approach on increasing sustainable productivity, adapt to climate change, and reduce greenhouse gas emissions? And how this ancestral knowledge, indigenous knowledge, can be inserted in the climate services. In one example, in Ecuador, we have a project, and is an agroforestry project on cocoa, and we use the chakra system, that is an indigenous knowledge system for cocoa and not only. The use of participatory approaches to generate, co-generate knowledge, and the use of farm and field schools to collect data, information, but also to inform people when this data and this information are elaborated, are analyzed, and provide equal opportunity for participation. Marginalized people, youth, gender are the most vulnerable people in this situation, in the context of climate change, and in agriculture more than in many other situations, in many other climate change situations. We need to give them the opportunity to participate from the beginning, to share knowledge, to share what are their experiences, what are their ideas. Voices from the field is absolutely important to elaborate a system where all the stakeholders are involved, where all the people can contribute in reducing the impact of climate change, and to increase sustainable agriculture, and how to use climate services to help on this goal. Thank you very much. I have here some references at the end of the presentation, but in the notes, in some slides, there are also other presentations, other references. Thank you very much.
Thank you very much, Federica, for the very interesting presentation. And the presentation will be available to our participants. So I will now take one question, and if anybody wants to ask a question to Federica, otherwise we move to the next speaker.
I hope to be in the time.
We're running a bit late, but it's something that often happens. So I would move straight to the next speaker, and I would pass it on to Massimiliano, who will be introducing our next speaker. Thanks.
Thank you very much, Luigi. We are now ready for our second special guest, Gabriela Nobre. She is early warning and early action analyst at the Climate and Earth Observation Team at the World Food Programme Research Assessment and Monitoring Division. She also works as a postdoctoral researcher at the Vrije University in Amsterdam, and also PhD on climate and weather risks. She is an expert in natural hazard, risk assessment, climate variability, hydrological and extreme statistics, and gained her competencies in several international and prominent research projects, such as the very famous SIMPREX project, an H2020 funded project. Now, Gabriela, as early warning and early action specialist, the WFP is working in drought, early warning, and seasonal forecasting in supporting the United Nations WFP operations. So it is a great pleasure for all of us to have Gabriela today in our Living Lab 2021. So, dear Gabriela, the floor is yours.
Thanks, Massi, and good morning to everybody. Greetings from Amsterdam. Thanks for the kind introductory words, Massi. So I will start trying to share my screen. Hope it works well. Okay, share screen. Can you see my presentation?
Yes, everything is working quite good.
Awesome. Okay. So let me just give you some background info for the presentation that I've prepared to you today. I've realized that it's a slightly different focus from the previous presentation we had. But today I would like to run you through some practical steps that we are currently developing at WFP for implementing the use of seasonal forecast information for drought management. And this methodology we have been developing for applications, especially in Mozambique and Zimbabwe. So I hope you find the presentation interesting and that you can learn something from that. Okay, so let's start. Let me see. Okay, yeah, great, it's working. So I'm not sure if all of you are familiar with the concept of forecast-based financing, but the idea is that we can take advantage of seasonal forecast information for reducing or mitigating the impact of an upcoming hazard based on information that is available ahead of time. With this information, we hope to be able to anticipate a number of actions that can be implemented and reduce the impact of a natural hazard in the population. So the focus today is especially on droughts, which is a slightly tricky hazard to work with. But basically, there are some set of steps that we need to kind of reflect on ourselves before we try to, digest the data and start working with the data. The first step that we need to consider before setting up this sort of system to trigger actions is basically a reflection on what kind of information do I need to get. So before setting up a trigger system based on this forecasting, the first question that I should try to answer to myself is basically what are the drought impacts and also when do they happen within this geography that I'm interested about. Within the forecast-based financing project, WFP has a strong focus on reducing the impacts of droughts on the agriculture system. And in the countries that we are developing this methodology for, that's Mozambique and Zimbabwe, the timing of the impact is also in connection to the raining cycle of the places, which is in this case it's a unimodal cycle that the raining period runs between October and March. So these are the two first sort of information that would be important for me. The second sort of questions is related to what are the actions that I can take in order to prevent these impacts, and when should this action be actually triggered in order to reduce these impacts. So within this, I can identify what is a window of activation for anticipatory actions that can still prevent some of the impacts. But in order to be able to activate some anticipatory actions, for instance, the distribution of drought-tolerant seeds, or the distribution of seasonal forecasting information, distribution of agricultural inputs, I also need to have all these type of actions procured and ready to be activated in the field. So I also need some buffer time in order to get the system ready. And the third component, then, it's related to the seasonal forecasting information. So what are what can we actually extract from the seasonal forecast information with skill, but also with lead time that would enable these systems to happen. So we know that seasonal forecasting information is available at the monthly time scale, but also what is important is to identify what is the window of interest that I would like to target with my forecasting information in order to be able to really understand what is the period that I should be focusing with my forecasting. So here you can see on the presentation, these are representation of the window of interest that we mostly are working with. So this triggering approach is relatively simple, and I apologize in advance if for some of you may seem relatively simple. But the first step, it's basically bringing together the data set that we want to work with. And this data set is a data set that would enable me to identify droughts in the regions of interest. The first one, and this data set is composed of two elements. Basically, one is the observation and the other one is the forecasting information. For the observations, we explore the use of the chirps. Chirps is a rainfall that blends both ground stations with satellite informations. And it's available near in real time in quasi all the world. And the forecasting information that we use is coming from the ECMWF Center. And we use daily rainfall forecast that covers a long lead period. The second step is basically then related to identifying when did the drought happen within my data sets that I explore. And the third step is a simple comparison between whether I observed has been actually forecasted by the system. So I'm going to run through these steps with you together. I hope you can follow these steps. If not, I'm always happy to reply some questions at the end. So with the forecasting information, I've mentioned that we have this focus on this window of interest. And basically what we do with these two sources of data set is to extract drought information. So basically indicators that can represent proxy for droughts. And from these both data sets, what I do then is to extract 4 classes of drought indicators. What these indicators are, they're basically, they're mainly calculated from rainfall anomalies. And the first one is the SPI indicators that I think many of you are familiar with, but is an indicator that basically measures anomalies around a norm or a normal condition in the region. And these indicators, we have been focusing on identifying anomalies that they happen at the multi-monthly scale, so at least 2 and 3 months. The second indicator is an indicator of dry spell, which measures the number of consecutive days without rain in a month. The second indicator, it's basically the starting of the season. And with this indicator, we want to understand whether the starting of the season is going to be delayed or not, given that the growing cycle in these countries are so short that any delay on the starting of the season might deteriorate the capacity of smallholder farmers to grow crops and sustain their livelihoods. And the fourth indicator is an indicator that measures a bit more of the agriculture droughts. It's called the Water Requirement Satisfaction Index. And this indicator basically tells us whether the water requirements of the crops has been fulfilled or not within the season. So here is basically just an overview of the indicators that we extract, putting in perspective of this window of interest that we would like to focus with. As you can see here, we have SPI of 2 months and of 3 months in the first and the second row. So here you can see the first SPI indicators that we extract and the last SPI indicators. In the third row, you can see the dry spell indicators that we extract per month. On the fourth row, it's the indicator of the starting of the season, which is just one indicator per season. And the fourth is the water requirement satisfaction that we try to understand at the end of the season whether the crop has been satisfied in terms of water or not. So basically, in total, what we are able to extract from these daily rainfall seasons, it's a maximum number of 17 indicators. And we extract all these indicators per district and also per drought severity that we would like to investigate. In terms of the forecasting information that we use a type of forecasting that is called December forecasting. That differs from most of the forecasting information that has been used on the past, which is a sort of deterministic forecasting. Deterministic forecast is basically you try to understand what the weather is going to look like a few months ahead, just with one realization of what the weather can look like. When we use a sample forecast, we then use this sample forecast is composed of groups of members, and which we should see as a range of uncertainties of that the weather can look like, rather than a single realization, so that we are better able to capture the uncertainties within the system. And this information is available each month, looking at the weather 7 months ahead. So basically, if I receive the information today, I'm able to tell you how should the season should look like within the next 7 months. So having a forecast coverage of the next 7 months. This sample forecast is composed mostly of 25 members. But in the recent years, there has been an upgrade, and you can retrieve 51 assemble members. And the way that you should more or less interpret that is that if all members of the forecast is pointing out to the same direction, then you have a high confidence in the system. If the members are pointing out to different directions, you have low confidence in the forecast. And here is also just a kind of timeline overview of what the forecast can cover. Within WFP, we try to already use some of this forecasting information that is available in May. Actually in April. So when you are in April, the forecasting that you receive should cover the next 7 months, which should reach up to the end of October. So October is actually the first month within this window of interest that we want to explore. So for instance, in April, we are able to extract indicators that they just reflect how October is going to look like. And as you move close to the starting of the raining season, you are able to extract more valuable information, so a higher number of drought indicators within this window of interest. So basically, these are just an overview of the forecasting coverage that we able to achieve with this type of forecasting information. And the way that you deal with this forecasting information and you extract drought indicators is similar to the one that you use with observations, but the difference is then that you need to repeat this process for each assemble member that you're working with the forecasting. And that at the end of your exercise, when you're extracting these drought indicators, you have a range of output values that you can expect with the forecasting information. So for instance, here you see that we have 25 different assemble members that we can then at the end extract 25 different outputs of the drought indicators. And then it comes next to the second step. Then what I need to do here then is start to observe when is a drought happening then in my data set. Is it when it's the indicator is below -1? Is it when the indicator is below 0? So this is an exercise that then would lead us to step number 2 of the process, which is then defining the drought occurrence in the data set. Ultimately, I would have to say that within this forecast-based financing ideal world, we would like to be able to work with droughts that they had a significant impact on livelihoods. But these would kind of require to move from a forecasting information that's more based on the impact. So this concept of impact-based forecasting. But in order to be able to achieve this type of impact-based forecasting, you also need to have a good data on the impacts on hand, and most importantly also observation of the impacts. And while these data sets are missing, and especially at the scale that we would like to implement these actions, the first step that we have taken is to identify droughts by their return periods. So according whether they happen more often or they happen less often. And for this, what we do is basically an exercise on standardizing the data set. And when we standardize the data set, we basically just put all the drought indicators at the same scale. And when we put these indicators at the same scale, we are then more able to compare them and also compare across regions, and we are more able to also combine these indicators if we want. So the exercise of standardization is relatively simple. So basically, you just put all the indicators at the scale of a mean value of 0. And you create this sort of curve. And underneath this curve, we can now actually extract probabilities or proportions of the data set. And what we can do then is to start playing around with different threshold levels in order to understand what is the frequency of the drought that I would like to act upon. So for instance, within WFP, we use the threshold of 1 in order to identify severe droughts. And the severe droughts are droughts that should happen within 1 to 6 years return period. And then we also have the more moderate and the more mild type of droughts that then use more moderate threshold levels. So in this example is 0.85 and 0.68. So now that I have defined these drought thresholds, I can then go back to my data set on the indicators of droughts and start to observe when has a drought happened on the past in both the observations and in the forecasting data set. For defining the drought occurrence in the data set, it's a relatively simple exercise for my observation series. So what I do is basically I put these 2 data sets together, the observations and the forecasts. And what we do, it's basically we set the trigger, or we set a threshold for the droughts and observe when has a drought happened or not on the past. And that's more or less what I do here in this example. So here is my actual droughts, and if I'm interested in this case to observe severe droughts, I basically just look at when in time did these indicators fall below this threshold of -1 if we are looking at SPI indicators, for instance. So here I'm able to identify with the ones when did that drought happen in the past. From the forecasting data set, then it's a bit more tricky because we are working with a collection of outputs. And what we want to do for all the forecasting information that we have available is basically to count the number of assemble members that are pointing out to a severe drought. And then basically it's what we do here on this column. So we have basically the probabilities of a severe drought happening. And when you have probabilities, then you need to start reflecting on when do I start to trust the model that is going to be a drought or not. And then for this step, we need to start defining what is the trigger. So when do I transform these probabilities to a drought, yes or not? So this process of transforming the probabilities to a drought, yes or not, is called setting up a trigger value. So basically what I can do here, for instance, is to start playing with a probability of 20%. So let's say whenever the system says that there is a probability higher than 20% for a drought happen, I'm going to consider that a drought is going to happen. And then that's what we have done here in this example. So we start as well identifying when is the 0 and 1s or the drought or non-drought events happening in the data set. And when we do that, we have basically 4 range of outcomes that can happen to the data set, which also would lead us to the last step of this triggering system, which is basically compare the observations with the forecast. And when then you start doing this comparison exercise, you will realize that 4 outcomes can happen. You can have success of the system. So it's basically when a drought happened and you were able to forecast. So this is called a hit. When you have not a drought and your system also indicated that a drought would not happen. So you have a correct rejection. When you have an actual drought and a drought not happened, or your system didn't forecast a drought, then when a drought didn't happen and your system indicated that a drought would happen, then you would have a false alarm. And when a drought happened in the past, but your system was not able to capture the drought, then we consider that the system has missed the drought event. So basically, with these 4 different outcomes, you can start extracting this sort of contingency table, which is very popular. I'm pretty sure that you all are very familiar with. And basically what we do is with all these trigger values that we start to set, we do these calculations on what was the success of my system, what was the errors coming from my system. And based on these numbers, I'm able then to extract a number of verification metrics. And these verification metrics will help me to identify what is the trigger value that it's optimum in a sense. And then what we do, it's basically to repeat this exercise on setting different trigger levels any times until I exhaust basically my possibilities. And then afterwards, I should have an overview. What are the potential triggers and what is the bias also related to these triggers that I've settled. And then at the end, when I've done all this exercise, then I'm able to design more of a decision making tables or metrics that kind of summarize the whole decision that we have done with the forecasting information. And in WFP, what we do is that after we have completed this exercise, then we extract these sort of tables, which we are able to say per district, per severity level of the drought, and also per forecast batch that we analyze. What is the chosen trigger in relation to the indicator that we want to use? What is the bias aspect, and also some remarks about the performance of the system. We also highlight in color code whether the system has a good skew or not. So for instance, you see in blue and in green good performance systems, and in red and yellow some sort of borderline system that's not so reliable. So basically, another thing important to reflect is that setting up this trigger is it's a tricky exercise, and I'll show you why.
Gabriela, I'm sorry.
Yes.
5 minutes or so to the end. I'm sorry for this.
That's in my last slide, basically.
Okay, thank you very much.
Yeah. So setting up a low trigger value, what happens is that my system is capturing all the drought events, basically. So I'm able to have a high detection percentage. But at the same time, I have many false alarms coming in my system. But on the other hand, if I set a trigger that is too high, I'm very likely going to have a low number of false alarms, but at the same time, I'm going to be missing in many drought events. So here as well, it comes an exercise on what is the priority that you should establish as a decision maker. Would you like to have a system that has a higher drought detection capacity, but that you should allow some errors to happen from time to time? Or would you like to have a system that doesn't produce so many errors, but at the same time, you might miss on some drought events? So this is an exercise that one should reflect when setting up this type of systems. So some key message from these presentations is that within this, what we hope one day to become a drought forecasting operational system, we are at the moment able to extract a maximum of 17 drought indicators. That also in this first version of the system, the drought is defined based on the return periods on the occurrence of the droughts. And that we also do the system verification in order to understand what is the limitations and the skew of the system. But at the end, the exercise on the selection of the triggers is always a compromise. What is the interest from the decision makers? Some next steps that we are hoping to develop with our system is to move from triggers that they are defined based on a single indicator to reflect more of collective evidence that a drought is being formed. So this is something that we have been working on. Our anticipatory action plans at the moment are designed only based on the results of the SPI indicator, but we hope to soon be able to update the system in order to build more of a multiple variable type of triggering system. And also we would like to have to move a bit the focus not only from the hazard but also to the impacts, and understand what is the link between these drought indicators that we are extracting to impacts that are also felt on the ground. And this is something as well that we would like to work in a very soon future. And with that, I can finalize here my presentation and say thank you for your attention, and hope that has been clear. If not, I'm happy to take any question.
Thank you very much, Gabriela. It was a very interesting presentation indeed. And let me highlight one key point of the amount of information gave us. It is the key point to build an effective climate service is to bring the choice, bring the moment of the decision making, the key point of decision making, with a very effective quality of information. That's the key, and you present this relevant work today to us, and so thank you very much for that. Thank you very much. If there are questions in the audience, I saw one hand raised by Maria. Please, Maria. You are muted, Maria.
And now it's okay?
Okay, okay.
Okay.
Please.
Thank you, Gabriela. I found your presentation very clear and very interesting. But I think about other factors that could be included to elaborate these drought indicators. I think, for example, on vapor pressure deficit, that is very important from the point of view of the plant. You know, is the relationship between air temperature and air water content. Another factor very important from the point of view of the plant tolerance to drought is the soil temperature, because that determines the root development, and also the soil water to keep water, the capacity of soil to keep the water from the irrigation. It depends of the soil structure and the texture. Sorry, for me it's complicated to pronounce that. But do you understand what I mean? There are other information that we can have from this climate database that could be used to elaborate some drought indicators more close to the crop behavior under a drought situation. I don't know if my question is, are you going to consider this climate data to elaborate these drought indicators?
Yeah, thanks, Maria. That's a very relevant question, and of course, it's very important to reflect on this too. I have to say that in terms of plant development, the indicator that we have been mostly related to that, to a certain extent, because has still its pitfalls, is the water requirement satisfaction index. I think you might be familiar with that, or maybe you crossed path at some point. But this indicator combines its use rainfall as one of indicators, but also use several other types of information. But it uses indicators, for instance, like evapotranspiration, and also crop requirements. For instance, what is the length of the growing season? What is the depth of the roots? So and also it's crop specific. So in this case, what we have at the moment extracted from, it's based on maize crop requirements. So I would say that for this first version of the system, maybe this is the indicator that would mostly reflect on some of the characteristics that you have pointed out. But definitely, I think if we are able to extract these indicators, that it's more specific to the agricultural types of impacts. from the seasonal forecasting information, I think we are very much open to also incorporate that in the system, because at the end, this system, it's the view of the system is to combine a number of relevant indicators. I mean, I've presented now 17, but the goal is to, to go as wide as possible for the system that also would incorporate a number of other indicators. We do plan to, in future, also incorporate indicators of soil moisture, and perhaps also give a better treatment on the way that we look at a specific area. So, for instance, looking at what's the crop type that is growing in a region also will help us a bit better to understand what is the source of indicators that we are missing out, and we should also include in the system. But yeah, thanks for the reminder. It's always good to keep in mind that what we have can always be improved.
Thank you. Thank you.
Thank you. Thank you. There is another question, hand raised by Tony. For Tony's, please, your question.
Good morning, Gabriela. Thanks for your presentation. It was really interesting, and I wondered, what do you do when you determine that there's a drought in a certain area that you study? What's the next step? How do you help people recover from it, prepare for it, deal with it?
Yeah, that's a good question, Tony. Thanks for that. There are a number of things that happens, followed by by what I just showed. I would say this is really just the point of the iceberg. So what we do when we develop this system is then to bring in, first of all, bring all these results to the stakeholders and put that on the table. So if we manage to agree on a trigger level that we feel comfortable with, that's the first step. This trigger then is going to feed a document that's called the Anticipatory Action Plan. And with these Anticipatory Action Plans, what we have, it's a clear indication of procedures that should follow once the forecasting information has pointed out that we should activate the system. And in these Anticipatory Action Plans, we, for instance, have the number of beneficiaries that we would like to support, the cost of the action, how many months we need to deploy these actions on the ground, and which are the types of actions that should follow to be implemented on the ground. At the moment, WFP is exploring a number of actions, and this is just what is, let's say, on my portfolio. But we have, for instance, the distribution of weather information, weather forecasting information. We have the distribution of water and cash transfers, and also the agriculture tolerant, drought tolerant inputs. For instance, seeds, but also agricultural inputs throughout the season. So these are the, let's say, the core type of activities that are developed. And ideally, these activities, they should happen at the certain times of the season, which these activities are still seen as relevant. So for instance, if you would like drought-tolerant seeds to reach the population in time before the planting starts, you probably would like already to start distributing these seeds in October, November, before the rainy season starts. But on the other hand, if you would like to distribute cash transfers because you detect the drought, for instance, at a later stage, or even if you implemented the actions were not sufficient to significantly reduce the impacts of the droughts, you still would like to support this, the livelihoods of people before their livelihoods deteriorate too much. So, for instance, you would like to distribute cash or food assistance or vouchers before the people start feeling an impact on the market, for instance, price spikes, which would also reduce their food security capacity. So there are certain activities that they happen at different timings, but let's say the technical part is just one component of several others that should follow.
Just a quick follow-up. What do you do with seed or water or any of the kind of products you distributed when the drought didn't materialize?
Yeah, I would say that this is more called the type of non-regret actions. These are type of actions that, regardless if you do or not, they're gonna have a benefit for the people that they are supported with. So if the actions are done, they are done, and they're going to be perceived as a benefit anyhow for the population that happened.
Okay,
great. Thank you.
Thank you very much, Gabriela. There is a quick question from Christine on the chat. I will read for you. Going forward, would you prefer a greater number of ensemble members or higher resolution simulation? Great. Great question.
Yeah, at the moment, I would say that a high agreement for the scale that we work would be more preferable. Also for the acceptance of the system itself, because it's a relatively new concept, which we would still, there's still the convincing. I mean, we are very convinced as a humanitarian organization that doing this type of actions is benefit for the population. But we also need to have the buy-in, for instance, from governmental agencies that they might have, for instance, limited resource, and they are not so happy if the drought does not materialize and the money has been wasted. At the moment, I would say that the focus on the higher agreement between the samples would probably be more appreciated than the final resolution, because also the types of actions that in the planning is also done at the district scale. So there might not be extremely the need at the moment for very fine resolution and forecasting information. So if we could start with agreement, and then we would find a way to refine the resolution, that would be a perfect match. But at the moment, if we would manage to, be able to produce more like accurate results based on more like a trustable information, that would be very appreciated.
Thank you very much, Gabriela. There is a last question from Ana Margarida. Please, Anna.
I'm sorry, I was muted. Hi, Gabriela. I was wondering if these initiatives are also combined with the efforts to plant more resilient plant species in these fields in Africa, to withstand these more likely to happen drought periods.
Yeah, that's a good question. So I think I would say the way I would reply to your question is that perhaps you should see this forecast-based financing as a range of complementary activities that WFP does in countries. So we have these forecast-based financing that it's really like small-scale projects that now has been pilot, and is really for like just part of the portfolio of activities that WFP is doing on the country. But in parallel to that, we also have more type of resilience programs in which these type of activities are more built on a constant base. So the forecast-based financing, I think we should see just as a complement to this more type of extensive resilience program that is done in the countries. And also in these resilience programs, there are a number of trainings and capacity build programs that are also done with the local farmers. So this is more like as a way to bring some of the resource for these activities that can be carried out earlier in time. But I would say that your point might touch more this type of resilience programs that are done in the countries.
Thank you.
Okay, thank you very much again, Gabriela, for the presentation and also the question and answer time with us. So we are at the end of this this session. So I leave the floor to Alessandro for the official and plenary and the plenary communication.
Thank you, Massi. Very quickly, because we are very, very late today, but we have had very interesting presentation. So 5 minutes break, and thank you very much to our guests, to Federica and Gabriela. Thank you very much. We reconvene in 5 minutes, so 12:35. And with the practical example by Matt Gold, and would like also to ask to the speakers, Christos, Raul, and Massi, to, if it's possible, to give presentation of about 12 minutes and nothing more. Thank you very much. Reconvene in 5 minutes. Thank you.
Okay, thank you. Bye-bye. Bye-bye.
Hi, everyone. I think that we could reconvene in now, more or less, because we are just a little bit late with respect to the original agenda. And so in this second part of the session, we'll have some practical example of how we can develop some climate service, and this was especially from the Met Gold experience. So we'll have the three stories about the three main pilot service developed in Met Gold, and we'll have as speaker and contributors three main actors for the three service. The first presentation is by Christos Giannakopoulos. Christos is from National Observatory of Athens, and he is very proactive member of Met Gold team, and is the leader with Javier of the work package on olive oil sector, and he has a very strong experience and such a long experience in the climate service arena. And so I'm immediately pass the floor to the witness to Christos, and thanks a lot, Christos, for your presence here, and the floor is yours. Thank you. You are muted, Christos.
Thank you, Alexandro. Thank you for this introduction. I have tried to share the screen, but can you see it or not?
Yes, thank you.
Because I don't see it, but
great. Yes, no, you can see we can see your screen. Thank you.
Okay, good. I'm going to talk about the olive oil sector and the data flow development that we did to meet the user needs, especially for the olive oil sector within Met Gold project. We built in the olive oil
Sorry,
sector.
Christos, could you just a little bit louder or closer to the microphone? Thank you.
Okay. Is it better now? Yes.
Please go ahead.
Okay. Within Met Gold, we built three main services for the olive oil sector: the dashboard, the Olivia platform, and the PBDM, the physiologically based demographic models. I briefly outline what is each one of the services that we built in the sector for the olive oil sector in Met Gold. The dashboard, maybe you will hear also in the other sectors, is a web-based application that allows the users to easily visualize, interact, or even download climate data and relevant indices, referring both to seasonal and long-term climate change projections. The Olivia platform is a web-based platform which includes a predictive pest management support system based on artificial intelligence, and the PBDM is an artificial intelligence-based application which captures the weather-driven biology of the interaction between olive and olive fruit fly. Briefly about the Olivia, because I will concentrate mostly on the data flow that we followed in the olive services. The Olivia platform is a decision-making tool designed for the olive oil sector that provides guidance to farmers and technicians to decide for the optimal irrigation, fertilization, and pesticide application. The tool helps the farmers to manage their production in an easy and efficient way by integrated advanced artificial intelligence, satellite data, and climate information data for past, present, and future. So you will see that it requires climate information data. In the framework of this project of Met Gold, this platform has been upgraded based on feedback received by engaging with olive oil sector users within the region of Andalusia in Spain, which is the target region within Met Gold for olive sector. The physiologically based demographic models are one of the key existing components of the MedGold project, and they are already part in the MedGold ICT platform. The climate data set that was used for these weather-driven simulations includes daily weather data for AgMera gridded observation climate data set, daily weather data provided by the region of Andalusia, and long-term future climate information. And then finally, we pass on the dashboard, which includes long-term projections and seasonal forecasts. And the flow is the climate flow workflow, the pre-processing climate data, bias correction, and post-processing. This is the general flow that we followed within MedGold. The pre-processing includes to find what data we can have available for the sector that we are used. And of course, we took climate cortex simulations of the recent past. We took also observations and EOBs for temperature and precipitation. And then we did an assessment of the skill of regional climate model simulations. Of course, then we observed, we obtained also climate simulations for the future climate, either for seasonal forecast or for longer term projections, but we performed additionally bias correction and further downscale to develop a bias corrected climate model data for present day and the future. And then after consultation with the stakeholders that were present in our project, we developed specific bioclimatic indices with maps and trends for the olive oil sector. If we go for the pre-processing for the long-term projections for climate change, we used multiple regional climate models and climate change scenarios in order to reduce uncertainty. So we used both a medium and a high-end emission scenario from RCPs, from climate scenarios, plus we downloaded various RCMs data that you can see below. We followed 5 sub-ensemble members from GCM RCM pairs. So we had a great selection of RCM regional climate model data. Plus, we used reference data sets in order to evaluate these regional climate model simulations of the present. So we collected station data for key variables from the Andalusia region in Spain, plus we used the EOBS gridded observational data set for the projections and the seasonal projection reanalysis data for the seasonal forecasts. For long-term projections, we used daily observations both for maximum and minimum temperature and precipitation. We used 7 available stations in the Andalusia region for the years 2001 until 2017, and we took the same variables from the EOBS, and we compared these against the station data to examine if EOBS could be used to evaluate the RCMs, the regional climate models, for the present day period. That was the procedure we followed in the long-term projections. Then for the seasonal forecasts, we used also a similar method, but here in seasonal forecast, maybe you will hear later also for the wine sector, we used in MedGold, the partners who were responsible for that, we used also a hindcast and forecast. You know that the hindcast in seasonal forecast is run for a previous time period and is used to calibrate the forecast comparing with observations, whereas the forecast predict the future conditions over the next 3 to 6 months. So the long-term projections, we talk about the 30 or even 50 years ahead. When we talk about seasonal forecast, we talk about the next 3 to 6 months. And we used several sub-ensemble members from seasonal forecast, the SMWF System 5, plus the Met of France and the UKMO also ensemble members. Then, as I told you before, we performed bias correction. For long-term projections, we evaluated the model's historical period against observations, the observations from Andalusia region and the EOBS gridded dataset. And we used only, afterwards, we used only the models that had a reasonable representation of the historical climate. And we took also from the models that had a regional representation, the ensemble mean of these models. Plus, we performed additional bias correction techniques to further improve the representation of the historical climate and of the extremes. And here I list the methods that we applied both for temperature and for precipitation. You see, some of them were similar, but for precipitation, we used additional methods. And all the methods for bias correction that we used can be found in the downscale R package, which you can get from this web address here. For seasonal forecast, the seasonal forecast also have to be systematically compared with the reference climate, either from reanalysis or observations to assess their overall quality. The reference data set that was used here was the JR55 reanalysis data, and the calibration method that is described in Toralba was introduced to reduce the bias. This technique can operate directly both on monthly and on daily data and is suitable for applications demanding predicted series with high temporal and spatial resolution. And then an important step after the bias correction in MetGold project for the olive oil sector was the post-processing. And this was to directly assess the user needs. So we organized 2 workshops in order to identify the end user needs regarding climate sector in agricultural practices for the olive oil sector. The first was the workshop was held in our champion partner, DCOOP, is a main participant in MetGold for the olive oil sector, with agronomists that took place, and they participated from the COOP and shared their knowledge on the user's needs, critical decisions, and further vulnerabilities in the olive oil sectors. MetGold partners took into consideration the provided information in order to develop the appropriate bioclimatic indices, and another workshop further was held online for the evaluation of the data services that were already developed within MetGold. The MetGold partners took into consideration the outcomes in order to address the real needs of the end users while developing the tool. Here is
sorry, 2 minutes.
Okay, here is a schematic of the post-processing for workshop for the user needs. You can see that for various applications, like for pest management, for soil management, harvest, pruning, the stakeholders, the DCOOP agronomists were mostly interested in weather forecasts, sub-seasonal and climate and seasonal forecasts. Whereas when we go to olive yield estimation, to pest management and tree spacing, that means how wide the tree needs to be planted in a climate change world, people were also interested in the climate projections, 20 to 50 or even 100 years ahead. And these were the climate indices that were decided to be used for the olive oil sector of particular relevance and importance to the sector. It is the mean maximum temperature, minimum temperature, number of days above 30 degrees in spring or 40 degrees in the summer, also total precipitation annually, winter and summer, and dry days when the precipitation is below 2 millimeters. And these were decided because in mind there was also the plant treatment, or irrigation, or fertilization for particular purposes, each index. That was from me, and thank you very much for your attention.
Thank you very much, Christos. And I think that you have provided a very good example on how to provide some sort of pilot service for, in this case, for the olive oil sector. We have time for just one question from the attendees. I don't know if there are any question or any. Please, Tony, the floor is yours.
Hi, Christos. Thanks for your presentation. I wonder, could you go 2 slides back in your presentation? Why is pest management a priority for decadal and up to 100-year projections? Could you explain that?
Okay, I think this came as an impact from the workshops, but I think that they will need to know whether new pest species are going to be present when the climate conditions change. This, I believe, whether will be a new pest that will be developed under climate change conditions, so to develop new pest management schemes. That is my impression.
That makes sense. Thank you. Thanks.
Okay.
Please, Luigi.
Yeah, if I can add just this small thing, and I forgot to turn on my webcam. The long-term information for pests also derives from an analysis we did in collaboration with the COP about good and bad years for olive production. That also included bad years for olive fly infestation. And Noah, and particularly Christos and collaborators went about looking for recurrence time for bad years. So that's another reason for interest. When you look at the long term, you kind of try to understand if very bad events are going to be more frequent in the future. And Christos, correct me if I'm wrong.
No. This was very valid observation, and I forgot to mention that we did a very useful analysis on a return period of very bad events. So bad event can be either a period, a year with very bad yield, or a period with very heavy pest infestation on crops, on olive crops. And we tried to project that in the future. So how frequent past periods of bad years are going to be in the future, whether the return periods of bad events are going to change under a future climate change world.
Thank you very much, Christos, and thank you very much for your presentation. Let me remind that all the presentations are, however, available in the web repository. And we can move to the pilot service of MedGold on wine. So it's a pleasure for me to introduce Raul Marcos. Raul is come from BSc and is one of the leader of the work package on the wine service, and is an expert of the seasonal forecast in BSc. Is one of the main providers of seasonal forecast for this initiative. And so please, Raul, let me know if everything is working. Yes, okay. We can see your screen. Thank you very much for being here, and the floor is yours, Raul. Thank you. You are muted, Raul.
Yeah, sorry. Can you see if I change the slide? Yeah. Okay. Thank you. So in my presentation, what I'm going to do is give you an overview of the path that led us to create the climate service for the wine sector and all the steps that we followed just to reach that point. So what was the overall objective in our project was, of course, just give a climate service. But what is a climate service? As we have seen in several presentations, and all of you might well know, is try to connect the world of the climate, that it's very scientific and very technical, with the application world, with the real world where there are the needs. And so the services try to match these both worlds into a service that gives tailored information for the needs of that specific sector. In our case, this is the wine world. In general, what we were pursuing in this work package, in work package 3, and that it was also common for the dashboards of the other sectors, was to develop a climate service for the wine sector, which were focused on 3 timescales: the historical diagnostics, the seasonal predictions, and also climate projections. So how do we achieve this? From the scientific and technical viewpoint, this is quite a straightforward ladder where there are specific steps that have to be followed, and just going one by one, we can reach the top, which is the climate service product. But this that seems quite straightforward from the scientific point of view needs of a whole interaction with the user. Otherwise, we risk of developing a climate service that it's not useful at all for them. So there is quite a big involvement of the user in this process in what we call different phases of co-design, co-development, testing, and also assessing the availability of the tool. So in overall, this process of laddering towards the different services is embedded in a circle of feedback and co-design, co-development, and this interaction with the user that provides the guidance and all the information useful for directing the technical and scientific work towards something that in the end would be usable and useful for the user. So in the first 2 phases that go together, which are the co-design and co-development, that's where we started. We established a fluid bidirectional communication between us, the scientific partners in MedGold, and Sorave, which was the user in the project, to facilitate the crafting of the service that could be tailored to fulfill the specific needs of the sector. And this is very important, and more specifically from the user point of view, for us, the scientific partners, to understand what is the user chain of decision-making, the understanding of the sectoral needs, and also from the user standpoint, just to which development points we need to focus more, either to be able to communicate accurately what we want to give to the user or what they need in us. So these interactions that involved the co-design and co-development of the wine dashboard that you might already have seen or you will see for sure, provided an ideal framework of fruitful exchange of knowledge, either for clarifying different aspects of the climate predictions and climate projections to the user, or introducing some key elements from the user decision workflow to us, the scientific partners that were maybe not so connected with this field of action. Which were these kind of concepts that we worked in these preliminary stages? I will give you some examples of them. For example, the first were the scales towards the different predictions can be applied, or the diagnostics, the historical diagnostics, what we refer to. So in this way, we could just distinguish between what is that comes from the present, that it's just the present, and the weather that we are not going to work on it in this specific project or service, and then the historical climate, that what we are going to give, and also the climate predictions to what to refer. Do they refer? So, for example, the seasonal forecast and the climate change projections. And another thing that we could introduce to the user is the difference in skill between the prediction, the forecast that they are used to use in their everyday work, which are the weather predictions, and the skill that they could expect from seasonal predictions, for example. So this difference is very important, because otherwise the whole decision chain just doesn't connect with expectations and what we are capable of offering at those timescales. So it's important that at the beginning, all this kind of information that for us could be very straightforward, that could be very normal or usual, then to be communicated properly to the user, just to start planning what are the decisions which can be take best advantage from this kind of predictions, climate predictions, which for example, in this example is seasonal predictions, and how do they differ from what they are used to. So with this information, then, as you've seen the similar table for Work Package 2, we could have this table of decision-making connected to timescale, which is very important, because then we can identify which decisions can be linked to what timescales. And this is just the starting point, the baseline from which the service can be developed. Otherwise, we cannot foresee which are the main strategies, or what we have to focus more our efforts. And as a result from these fluid interactions at the beginning, what we identified as for just more specifically for those decisions and timescales, we identified 3 different layers of complexity in the information that could be useful for the wine sector. And these 3 layers of complexity are at the baseline, at the essential climate variables, temperature and rainfall. Then another layer which is built upon the one below, which are the bioclimatic indicators. Here you could see the different bioclimatic indicators that we have used in the project and identified that could be useful for the sector. And finally, the risk indices that are aggregating the information of the bioclimatic indicators into specific indices that answer specific questions related to pest control or to the influence of the heat on the crops, that are very specific to the sector and that are developed specifically from these different layers of simpler information. Once we completed that first stage of co-design and we were involved in the co-development, and the co-development advanced, then it comes also the testing phase, which was here as we start to develop the service. We need continuous feedback to just direct and to constrain the development to what is really useful. And to do so, during the project, we attained this through 2 different actions, which were the so-called dashboard sprints, where the developers, scientific partners, and also the users met just to identify where some maybe bugs or some developments should be directed, where the most effort should be directed, and also trial sessions of feedback that's already organized within the technical experts of the company, just to identify different also this information that at some point come to the dashboard screens. And so that's how we, in the end, reach that the wine service tool. That's what you think. Sorry, 2 minutes.
2
okay.
minutes. 2 minutes.
Okay, thank you, Alessandro. We reached the final this version of the tool that you maybe already have seen or that you will see. But once we reach that point that where we have the tool and we have it more or less working, there is another phase that still needs to be completed, which is assessing the added value of the tool. So, and here, which is the final step of our development here in NetGoal of the wine service tool, we assess it through different points of view. One of them is through interaction with users, either through surveys or continuous feedback collection, as we can see here. But there is also another point that's here is the usability of the tool, how useful it could be. And then is the impact of the using of climate predictions has on the strategic planning. And here is where there is another approach of assessing the added value in the context of decision making. For example, in the case of seasonal forecast, that's depending on the skill, and if the forecast is above average, normal below average, when is best to make a decision. And I think that's it. If you have any questions or.
Thank you very much, Raul, for this quite interesting overall landscape of the pilot service on wine sector in NetGoal. Yes, we have already met the dashboard in other moment, but you have provided a very comprehensive overview of how we developed this kind of tool. There is a hand raised by Wafai. Please, Wafai, the floor is yours.
Yes, I have a question for both presentations, for Christos and Raul. So thank you very much for the presentation. It's very interesting. So my question is about the skill of the seasonal forecast of these products, and also the feedback from users. Are they satisfied by these products? Thank you very much.
Okay, yeah, that's an interesting question, because that's just the most single critical point of the service, which is the skill of the seasonal forecast, how can be used to retrieve value from using it in the decision making. And that's been the complexity of understanding that this still can give value is the first step, that where the communication between us and the user was very intense, and just to be sure that everyone understood what are the limits of the seasonal forecast, but also where are the potentialities and where is the connection between this potential and the decisions that could take advantage of this potential. And that's the last slide that I showed you. That's one of the examples that we carried out during the project, where we try to identify a decision and give a specific example of what would be the economic impact of using seasonal forecast in their decision working flow. And the overall impression is that there is the possibility to introduce this forecast inside the decision making, but there is a work that has to be done. It's not straightforward as if when we use meteorology.
Thank you, Raul. I don't know if Christos want to add something.
No, I think Raul covered completely the question on the seasonal forecasts.
Okay, thank you. Thank you, Raul, and thank you, Christos. And there is time for another quick question if there is something from you? Okay, if it's not the case, I think that we would like to thanks again Raul and Christos. And now the last obstacle before us and the lunch is Massi. You already know very well Massi. In this case, Massi is a speaker about the pilot service on the durum wheat, and he'll provide an overview on how we develop the pilot service for durum wheat and pasta sector in MedGold. Massi, please, the floor is yours. Thank you. You are muted, Massi. You are still muted, indeed.
Yeah, I'm sorry.
That's better now.
Okay, sorry for that. Let me start the presentation mode. I will cover the third pilot service, which is dealing with durum wheat and pasta. And I will go through an overview of the steps, but also the tools that we developed during this period of the MedGold project. First of all, let me show you briefly the design of the innovative agroclimatic system for durum wheat. We started essentially from the very beginning in the design, in the proposal of the project, since some of the tools that we developed further during the project were present also at the very beginning, so they experience a further development during the project. So our intention was to cover the past, the present, the future timeline with a starting point from observation to cover the agronomic data, climate observation, and forecast, for example, coming from the Copernicus, using several already present models, such as the Delphi crop model or WAFOST, along with this very complex decision-making tool called granoduro.net that you saw in action from the presentation from Horta for the case study, and a risk evaluation tool which is called ClisAgri, and again JRC, our partner, and Andrei Zegler showed us the more details on that. And in a very complex but also long interactive development phases, we analyze some key points and we try to develop these tools in a more mature phase in terms of the designing of an innovative agroclimatic system for durum wheat. And then we face the action of using seasonal forecasts, decadal prediction, but also climate projection to provide useful information, salient information for different kinds of users. So actually the core of the system is made by 4 different tools, as I already mentioned them. They are granoduro.net, Clisagri, Delphi, Wophos, T-Crops. Each of them are managed essentially by one of the partners of the MedGold project, and they are dealing with different aspects of the managing the agro food system related to the durum wheat. We will see a brief detail, but briefly in the next slides. The general approach, as you already listened, was essentially based on an interactive procedure. Several different phases in which we will try to ask and to get the knowledge, but also the needs from users, and then we propose them our ideas of how to develop the system, and then through an iteration of meetings, we will refine these ideas through the time. Let me highlight a very demanding but also critical key point, which is the climate data processing package. This is one of the gaps that at the moment are existing in the framework of climate services, of delivering climate services, and that is covered by the MedGold project through a very massive efforts to get the right information from the right sources to provide this refined information to the right tool to be delivered to deliver the final information. So this is a critical point. Sometimes is not so evident, but it is still there. A complex structure of getting and manipulating data from different sources for different goals. Granoduro.net was one of the main tool used in MedGold. It is a decision support system for durum wheat cultivation, simulating crop development, disease risks, weather balance, giving soil and fertilization, weeds management advices. It is thought for farmers, elevators essentially in the barilla supplies chain. As you can see here, you have now 4 different new key information regarding the phenology, but also some projection on seasonal indexes, and also to the longer time scale regarding the climate projection. So information related to the climate projection. All this new information are available for all the farmers that are already use the granoduro.net from Horta. Clisagri is a dynamic crop phenology model with a suite of dedicated agroclimatic risk indicators. It is an open source package designed to bring the key information to crop producers during different stages of the crop growth. Here you see some examples, and two of them are coming from 2 very different reference points. The first is on the left. You will see the seasonal forecast application of Clisagri, while on the right side you will see the application of longer time scale of the same tool. So a versatile tool to produce key information, essentially for sensitive crop phenological stages. Then we have the Delphi model, which is a mechanistic modeling system for simulating durum wheat yield and biomass. This was a very effective tool used by Barillas insofar to manage their decisions in not only in Italy but also in the Mediterranean. And during the MedGoal phase, the MedGoal project, Delphi model was enriched with the potential viability of seasonal forecasts. So he expands its capability of simulating the durum wheat yield and biomass with the latest and most prominent information coming from the seasonal forecast science. And this information is now available for Barilla through the already established link and connection and tools, and through the tools they are used to adopt in their decision-making processes. Then it was developed, the Wofost ECROPS, another very interesting tool thought essentially for the policymaker, users as policymakers, since it is able to provide a service for longer time scale, from decadal to future climate projections, and it is an essential tool. Again, it is an open access tool that could be used for planning on this longer time scale. So this is essentially a very brief overview of the tools we developed during the MedGoal project. Some of them were shown you in more detail in the previous sessions, but of course, for any questions and any interest about them, we are more than happy to answer to you. So thank you very much for your attention.
Thank you very much, Massi. Perfectly on time. And so there is time for some question on this overall presentation about on how to develop something for the durum wheat sector. There is a hand raised by Tony. Please, Tony.
Thanks, Massimiliano. I wonder, comparing the three presentations for olive, grapes, and durum wheat, it felt like durum wheat was the most sophisticated process, and I wonder if that's just my perception, or if that's true, and if it's true, why is it?
Well, actually, it is true from several points of view, but the reason was essentially linked to the fact that some of the tools were already present and was, how to say, the gift of partners that bring to the project at the starting point. So some of them were already established as a tool, but tool for example, for the agrometeorological framework of reference, not used as we then developed for the seasonal forecast time range. And other tools, for example, Clisagri, just to mention one, was essentially a joint effort between Horta and JRC to develop an effective and easy to use tool coming from the phase of listening from the needs of users, both farmers, technicians, but also policymakers. So there are a very heterogeneous landscape of tools, and for sure some of them are more complex than others. But the key point is that they were already established as also a commercial tool, with a background in terms of delivering a service. But during the MedGold project, they acquired new functionalities in specific time frames where they didn't work before the project. So they acquire a more option to be used, essentially in the seasonal forecast time frame and in the future projection time frame. So the answer is yes, but because there is a background behind this, some of them.
Yes, thank you. Thank you, Massi. If I could add a few words. Yes, it's exactly this the point, that in MedGold we have a very widespread of service and even of widespread of different approach with the users. In this case, as Massi said, we already had some technical solution implemented. The path is completely different from the other from the other sectors where we had to develop something from scratch, and so it's completely different approach. And this is something quite common in the climate service issue, I suppose. But it's very relevant point, and thanks, Tony, to have highlighted this aspect. I don't know if there are any other question. Okay, if it's not the case, I think that we could close this session, a very long session, but with plenty of information and food for thoughts for the work of the team. I would like just to remind that next week we'll have the end-on session completely devoted to the teamwork, and next Thursday in the session about testing and visualization of climate service, we'll have a block devoted to the sprint presentation by the teams with the problem holders. So there is an important milestone for the works of the team. So please keep in touch with your team for the work that should be planned or done in the view of this relevant appointment for the Living Lab. And thank you very much. The material is already available in the web repository, and we will also include the video of the session soon. And thank you very much. Have a good afternoon, and we'll meet again on the next Monday. Thank you.
Bye.
Bye-bye.